Okay, so any of you that know me understand I'm a power guy. I'm all about the power. And I got to tell you, every time I look at a Wisconsin car, I get pretty excited because they know power. Unfortunately, this car isn't powered by gasoline molecules. It's powered by electrons. But I've come to understand that I can maybe get even more excited about an electron-powered car because this car is pretty special. It's got 4 motors on it, and it, when the controllers are working correctly, it practices electronic differentiation, or vectoring, torque vectoring. And when you think about this, it's pretty unique because I've been involved in motorsports for, I don't know, plus 40 years or whatever, and particularly involved in rally and road racing, and in rally in particular with a small little turbocharged 4-cylinder all-wheel drive car. The drivetrain is really important, and the characteristics of the front, the center, and the rear differential on your rally car really determine how well the thing is going to corner, accelerate, brake, and maybe even flip over if you're not careful. All of the stuff that I've learned over my career pretty much goes out the window with this car because there's not a mechanical adjustment for the torque vectoring on this. It's all electronic. And some of the characteristics that you can get torque vectoring to do via electronics is far beyond what I could have ever dreamed about back in the rally days with purely mechanical torque sensing devices. Wisconsin pretty well went on a limb. Well, they didn't really go out on a limb. They had an idea for what they wanted to do, and they executed it extremely well. So their car weighs 506 pounds. It's also a pretty, for being an electric car, 506 pounds is pretty special. It's pretty lightweight. They paid particularly close attention to the torque charts and checklists that go with the electric motors, and they did a detailed gearbox loss analysis during drivetrain loads. So this is not just an electric drivetrain; it's an optimized drivetrain that they paid particularly close attention to. They sized their motors based on loads, and the motor selection is really well understood. They didn't just look at 1 or 2 or 3 motors. They looked at every motor they could find. And I guess at the 300 volt range, from what I understand, it's kind of slim pickings. It's a whole lot better when you get to 600 volts, and we'll keep lobbying the SAE to get back with the 600 volt standard, but that's another argument for another day. So let me say that again, SAE. I think that the students in this room really want 600 volts, right?
Yeah, want it.
I hear take the restrictors off too, is that what I heard?
Okay, so Wisconsin's a pretty mature team. They've been around the block once or twice. They know how to find their way to the winner's circle with the gas molecules, and I'm sure that they're going to do the same with electrons shortly. Won't be this weekend, but you know, they had, well, from what I understand, they had a control board center on the 2 front motors, which put them on rear-wheel drive only, but they still were able to torque vector the 2 rear wheels, so there was torque differentiation electronically controlled. They have a very thorough understanding of loads, and this comes from all of the experience that they've had over the years doing some really great gas motor cars. This car is extremely stiff, low compliance structure, and they pay particularly close attention to lightweight, strong design. Their targeted frame stiffness is very well understood. The team's pretty switched on. The car is very comfortable to sit in, although the 5th percentile female would not agree with me on that. But if I had to drive this car, I guarantee you, with all electric motors running, I could make this car go really fast. It excites me to be looking at something like this that, you know, it's the way of the future. The one comment that maybe didn't surprise me, but you get these little pearls out of design judges every once in a while. Here's one. Great depth, understanding and data confirming of calipers, okay? Best I've ever seen. This car has some rather unique front brakes on it because it's got wheel motors that are on the inside of the wheels, and they've got small 4-inch diameter, 1/4-inch thick steel rotors. They're hardened stainless steel rotors on the outside of the wheel with a custom designed 4-piston caliper. Now when you drop the rotor size down on a front rotor application, you got to start squeezing this thing a whole lot harder because you've lost leverage because of the small diameter rotor. They realized this. They selected a particularly robust brake pad from a BMW MotoGP bike that will withstand the extreme pressure. So instead of increasing the line pressure to the front brakes, they did it in a very sensible way. They put 4-piston calipers on, kept the line pressure under control, and brought the brakes into full integration with the car. It's a pretty nice, well thought out set of brakes integrated in with the wheel motors. I'm going to turn it over to Dave, and we're going to have a little interview with Wisconsin-Madison.
Yeah, a couple things that was really interesting about this car, this team, is the documentation is just incredible. I mean, if you ask, they got a binder or a whole pamphlet about it. Like they've done this competition before sometime. They've won a number of times, so they know their way around. But it's something for all you to realize is there's only so much you can communicate to us as judges in 45 minutes. And yes, they'll show pictures, diagrams, equations, everything is right there, rather than trying to just say it verbally. So very good at that. So they're really quite prepared. They're also working hard at getting the underclassmen to be more and more involved in the team. So you don't wait until you're late in your junior year or senior year to really get going. They're working at making it literally. Students from 3 different classes typically are working in the car pretty much in earnest. They do a good job of training their drivers using the data. They've switched data systems. They actually had a vector system, which actually is a little bit clunky, not as elegant as I probably like, but they did it because they had a lot more processing capability, and they're looking to grow with it to do a lot more networking with CAN, and I think they'll do well with that. As Steve mentioned, the torque vectoring they do, it's not just that they did it, they understood the strategies. They showed vehicle dynamics-wise why they could apply more current to a corner and expect a difference in terms of the way the car handled. And they just had that down right. I'd like to bring Billy and James up from Madison. Okay, James is the driveline lead, okay, or train lead, I should say, and Billy is more the technical director, okay, and handles the all-wheel drive systems, okay. First off, tell us more about your all-wheel drive system, why you chose to bother. You know it was a weight penalty to do it. Why did you go with it? You went to compact motors, but it's a lot more complexity. Why did you choose to do that?
Yeah, so moving into building electric vehicles at our school for the first time, we really wanted to take advantage of everything an electric vehicle has to offer. So now you have the ability to put power in all 4 corners of the tire, start utilizing the full capability of each tire that you have in both cornering and in acceleration. So our design process starts for whether it's our combustion vehicle or the electric vehicle in lap time simulation, figuring out what size motors we should have, whether it's an engine or an electric motor for our vehicle. So figuring out based on vehicle dynamics, what size motors should we have, where should we have them, and how should we implement them. I think the most exciting thing we did in this vehicle is we set a really aggressive timeline saying we're going to go all-wheel drive in our first season, but how we did it was really breaking it into 2 separate systems, an in-hub motor system in the front and a rear drive unit inside the rear frame. So me up front, James in the rear there. So basically doing that was allowing us to build a system that we had a lot of reliability with, so we could run rear-wheel drive no matter what happens, but also be able to take full capability of all 4 motors. So it was a little unfortunate we weren't able to drive all-wheel here at this competition, but all of our testing, we got about 61 miles with the vehicle running all-wheel drive and implementing those systems.
Yeah, you validated it well. It wasn't just, we've done this, trust us. You showed the data, you actually had done it quite well. The other thing you focused on was more for design for manufacturing, okay? And you understood the cost implications of doing it right. Comment on it a little bit more, because you had to go through a whole bunch of servicing with this car in the last few days, and you came darn close to getting back together for endurance, or most people just would have given up. So, comment on your servicing and your manufacturing focus.
Yeah, so two things there. Serviceability. Obviously, we wanted to build a robust system that we could confidently bring to this competition even when different parts break. So being that we're one team that builds two cars, we work closely with our combustion program to develop suspension geometries and a monocoque that we can use on both vehicle systems. So an example of serviceability is if for some reason the front motors were to fail, we would be able to take the entire front wheel off at the A-arms and put on the combustion vehicle's front wheel with their brake setup. So we could bring just a purely rear-wheel drive car to competition. And there are all sorts of little examples about that. And then we also want to optimize for our vehicle systems. So from the back of the monocoque, which is the same with the combustion vehicle, we actually have custom built and custom designed rear frames for each one of the vehicles to optimize for the specific packaging that we have and the packaging needs that are drastically different between an electric car and a combustion car. From a manufacturability standpoint, I think everybody's familiar with this in this room. At some point, you've got to be the one who's actually going to be building the thing in front of you. So whatever you're doing on CAD, the harder you make it, the harder you're making your life when you have to build it. So we pursued several different manufacturing techniques for certain components on the car. One of the things I'm most familiar with is the rear drivetrain. We use CNC milling, 6061 aluminum, as I'm sure most of you do as well. For the center portion of the housing, it would have been a 4-inch thick piece of billet aluminum that I would have started machining down from, and that sounded terrible. So I started looking at different opportunities with 3D printing using DMLS out of aluminum, as well as lost foam casting, and I pursued both of those opportunities to create a lost foam cast center portion of my gear housing, as well as a 3D printed thing and portion of my housing. And I was able to directly compare the pros and cons of each one of those processes and save myself a huge amount of time by just having to do a small amount of post-machining. So, always thinking about how can we streamline our processes and learn as much from these experimentations that we're doing.
Yeah, it's so important because you want to be able to be in a competition and run, of course, and you didn't give up. I mean, it was always quite close. I saw what was going on this morning. You're sitting there getting some moisture that got in your accumulator. You're like, hey, how'd that get there? I've never seen that before. And you were working at it. One of the things that impressed me when I talked to you on Thursday a bit and also a little bit yesterday is that when you went in validations, there were cases where the validation didn't match what your predictions say by quite a bit. And you said, what do we do? And he actually came back and said, hey, this is our learning process. This is our aha moment. We had to just push it through because that's what our computer model says. You came back and said, no, we obviously had an error in our model somewhere, and you didn't just push it through. So that's part of the learning process. I said before, someone's got to fail a little bit to kind of get to the next level again. So, again, fantastic. I'll be quite honest with you, what we've done with this car is really reminding me of what we've seen with some of the European cars that have gone over done well. It's not just the physical car, as Robert said, just the way your old team dynamic is working. So, again, kudos to you, and you deserve to be up here. Congratulations.